Okay, let's get started. So today we'll continue with synchronous machines. Then after that, we'll look at the transformers and induction generators or induction machines. Right, so last time for synchronous machine, we basically ended up with this model. So if we have a synchronous generator, right, so let's say, so if we have a synchronous generator, electronically, or electrically, the way we're going to look at it is there's some voltage source sitting behind a reactance. Right? So there's some equivalent field voltage, and then there's a synchronous reactance representing the reactance coming from the fact that we have sort of coils of wires in this machine. So this is our synchronous generator. And then often what we'll have is we'll have a synchronous generator connect to the grid. So often we'll have synchronous generator connect to the grid. So if you're one generator and you're looking at the grid, last time we said that from the generator's perspective, the grid essentially looks like a very stiff voltage, right? So the grid from the generator's perspective looks like an infinite bus. So electrically, this means that I have some generator or some synchronous reactance. Then I'm looking at the grid, and this is the grid, and this is called an infinite bus. And this infinite bus model essentially says the following. Vt is a fixed voltage, right? So this is not impacted. EF or the power generated. Okay. So for the infinite bus model says of a generator, I'm sending power into the grid. Right? So the way the grid appears to me, because the grid is much larger than a single generator, is just some fixed voltage source, a fixed voltage. Right? So some fixed voltage component that will just take in this power. And whatever I send will have no impact on the voltage of the grid. Okay, so it's called an infinite bus because you can think of as infinitely large, right? As infinitely large. Okay. So when we come to think of the operation of the generator, basically the infinite bus can be seen as a fixed, right? So infinite bus appears as a fixed voltage. So Vt is fixed. So this appears as a fixed voltage. And then current into Vt means that the generator is sending power into the grid. Okay. So this means that we know the value of Vt, and often we know the power that the grid wants from this generator. So the goal is to figure out the voltage of the generator and figure out sort of the angles in the system. Right? So the idea is that when you have a grid connected generator, Vt, this is fixed by the grid. And then for EF, you can compute through this equation. Right? So then the goal is to deliver some power to the fixed voltage Vt, Vft. Any questions for this model? All right, so this is our infinite bus model. So the idea now is to figure out how much power I can deliver to the system, right? And figure out, is there a maximum power I can deliver to the system? And what that, how does that depend on the voltage and angles? So if you want to figure out the power delivered, right? So always what we care about most times is the power delivered to the terminal. Okay. So we care about sort of power okay. When we talk about power, we almost always talk about what P and Q shows up at the terminal. Not so much about what is the power coming out EF. So if you look at the calculation, then the complex power delivered to the terminal is just the current, right? Voltage multiplied by the complex conjugate of the current. Right. And since we always want to take VT as the reference, so VT 0 degrees, because that's a natural reference to pick. We pick the grid as a 0 degrees reference. So for equations to work out, a bit easier to work with the complex conjugate of the power, S. So instead of conjugating the current, we'll conjugate the voltage, but then the voltage just has angle 0. Right? So that makes the equation a little bit easier to work out. So if you look at this equation, this is just VT. And then we can expand EF. This is EF cosine delta. So EF is EF angle delta degrees. Cosine delta minus EF sine delta minus VT divided by JXS. So we can work out what this equation is. This is simply just VT EF over XS sine delta plus J VT over XS VT minus EF cosine delta. Okay, so this is the equation, the way equation works out. And we get this is P, this is minus Q. And this is written out again here. Okay, so you do some simple calculation, and at the end of the day, you get P. The active power is given by a term with sine of the angle, and the reactive power is given by the term that involves cosine of the angle. Any questions about this one? Okay, so we'll be seeing a lot of this equations. We'll be seeing a lot, especially the one with the sign. Right, so this, and when we have three phase, right, so we put a 3 in front of everything. We put a 3 in front of this. And thing again to note here is here VTEF are the per phase voltages. So if given in line to line, divide by √3. Okay, right? So there's 3 times the single phase equivalent power. So VT and EF are per phase voltages. Then you just multiply everything by 3. If they're line to line voltages, then you have a offset of √3. Right? So you divide the voltages by √3. Okay. And then when you look at these equations, the important one is actually the P equation. So the P equation is an important equation because as 3 times the voltages divided by the product of the voltages divided by the synchronous reactance times sine of delta, right? So there is a peak amount of power you can transfer. Okay? So there's a peak amount of power. basically, this says that the maximum amount of power you can transfer is 3 times VT times EF divided by XS. Okay, so this is the maximum you can ever transfer from your generator to the grid. So this is interesting since that this is actually says often you're not limited. You're actually not limited by the amount of mechanical power you can show me. Right, so this is the electric model. So it says describe the whatever mechanical power you can get into this generator. Electrically, the maximum power you can pull out of it is 3 times VT times EF over XS. Okay, so the circuit puts some limit on the amount of power you can transfer. Right, so if your voltage are set at a certain level, you have some excess, then there's the maximum power. There is just a power you can get to the rest of the system. Any questions about that?
I've got a question.
Yeah.
So for the P max, you said it's multiplied by the EF. Is that like the E total of the sine part and both the cosine parts also, right? For the P max?
EF is just the magnitude of the field voltage.
Oh, okay.
Right,
So the
so
component sine and cosine is not counted.
No, so you maximize this value, right? This value has a maximum when sine is at 90 degrees, right? When delta is at 90, and sine of 90 is 1.
Oh, okay. Thank you.
Right, so you maximize over this equation. Right, so P max, this is, right, so delta equals 90 degrees, then delta is 1. Right? So that's when the maximum occurs. Any questions about this? Yeah, go ahead.
Yeah, when you're trying to maximize the power, then you're trying to maximize EF and minimize the inductance, but they also depend on each other, right?
So you cannot do much about XS.
Okay.
That's internal to your machine. They're not much, they're just depending on the wiring of your machine. So there's not much you can do about XS.
Okay.
Yeah. So XS is typically just a fixed number. And EF, there's only a certain amount of things you can do to EF. So your generators cannot generate a very high voltage. So this is basically the power you can output. Right? So there's a maximum EF you can operate at. Any other questions about this equation? Okay, so then if you look at this equation, there is immediately a question. Because from the grid perspective, as you often say, I want some power. Of course, you cannot ask for more than the maximum power I can deliver. But then let's say the grid, wants some power, let's say here. Right? Let's say this is the power required by the grid. Then this crosses my curve at 2 points. Which point should I operate on? Right? So let's say grid requires some power less than P max. Then now it seems I have a choice. Right? I can pick there's 2 angles I can pick that will deliver the same active power, let's say, to the grid. Which one do I pick? So which one does the generator operate? Right, the generator has to operate at 1 angle, right? It cannot operate at 2 different angles at the same time. The generator needs to pick 1 angle it operates at to deliver this power to the grid. Does it operate at the angle, the smaller or the larger angle?
Smaller?
Why?
Not sure. Just seems logically it would be less than 90.
Right, so it turns out you want to make sure you operate at a smaller angle. Or often as you stay far away from 90 degrees. Even though 90 degrees, you get the maximum power. Often your actual power rating will be much less than the 90 degrees. how then the sort of the theoretical max to make sure you operate at this point. And so the goal is to offer, this is called a stable operating point. And we can sort of then, so now we'll talk about why we want to operate at this point, right? There's sort of, we have, losing tuition smaller is better, so 0 is you don't want to be too far from 0. But let's see why. Let's see why this is. Yeah.
What is this angle again? I'm sorry.
Right. So let's say your demands on power, right? So I can draw, this is the maximum power I can deliver. So let's say the grid wants you to deliver P1. Okay. Right. So the grid wants you to deliver, let's say your maximum is 100 megawatts. Now the grid wants 75. Right? So then the way you deliver this power is you solve this equation, PE equals to 3VT times EF over XS times sine delta. Right? You solve this equation to figure out which angle you should operate at to deliver this power. Okay.
I guess I was asking like what this angle represents, like where we got that angle.
This angle is the angle of the equivalent field voltage.
I
So
see. Okay.
Yeah, this is the angle of the equivalent field voltage. So this sine, right? So remember this derivation. This is saying that VT is at angle 0, right? That's our reference. Then the voltage source, EF, has a non-zero angle now. And this angle shows up in the active power equations, like this.
Okay, thank you.
Okay, any other questions about this? So it's very important to ask questions now. You'll see this equation a lot. Like synchronous generator, most of the time is dealing with this equation. And believe it or not, this is still an actual research topic, actually, dealing with this kind of equation with science in it. Okay, so if you have a question, please ask now. Right, so you have this equation. This equation determines the amount of power you send into the grid, right? So if you want to send some power into the grid, turns out there's 2 angles you can operate at to send the same amount of power, right? One is here, one is here. And we want to show that this is the point you want to operate at. You want to operate at a smaller angle. Any questions with the thing we want to argue? Right? We want to argue that this angle is, there's some difference basically between the left angle and the right angle. Okay? Between the angle with the smaller value and the angle with the larger value. Even though they supply the same amount of power to the grid.
Wait, so they both supply the same amount of power but different angle. But you said there's something different. Can you explain like a little bit more?
Yeah. So next we'll explain why they're different. But as the are the angles clear, right? Are we clear up to here?
So the Pmax is not stable, right? And then when we lower down the angle a little bit to P1, then in that case the generator is stable.
No. P1 is the amount of power I need to supply, right? P1 is this horizontal line. I have 2, right? So for any P smaller than P max, I can operate at potentially 2 angles, right? There's 2 solutions to this equation. Okay, right? So this is suppose, right? So let's say, P max is 3 VTEF XS sine 90 degrees, right? This is my P max. Okay, so now let's say we want 0.8 P max. Okay, so then we need to solve 0.8 equals to sine delta. And there's 2 solutions here. Right? There's 2 solutions. Right? So if you just solve the equation this way, you have two, solutions that solves the equation point A equals sine delta. Are we clear on this part?
Yeah, and then I just have one more question.
Yeah.
So why do we get the max at 90 then? It's so not it's at when we're at 90 then EF and VT are 90 degrees out of phase.
Yeah, so sine is maximized at 90 degrees, right? Power
I
with-
guess like more like intuitively, like looking at the circuit, why does that 90 degrees make sense?
Oh, because you're dividing by reactance. You're dividing by JXS. So you want
Okay,
the 90 degrees, right? You want the J to cancel.
I see. Okay.
Okay. All right, so there's so there are two solutions, right? We want to figure out then, but we need to pick one, right? So we always need to pick one to operate at. So whenever you have two solutions, there should be another additional principle to pick one of them. Right? So the way we pick one of them is to think of power balance and think of what happens when you change the power a little bit. So when you look at power balance, basically what we have is, I have some mechanical torque, right, put into the turbine. So ignore the loss for now, suppose there's no loss. So think of, we have some mechanical torque I put into the turbine. The turbine is putting out some electric power. So the way I can think of in steady state is that I have, the mechanical torque equals to the electric torque, right? My mechanical power input is equal to the electrical power, sending to the grid. And then everything operates at this sort of constant steady 60 hertz speed. Okay. Right, so power, right? So you can think, so power is the rotational speed times torque. So here, so power equals rotational speed times torque. So basically, input power equals output power means that my frequency doesn't change, right? So torque being equal means power, and frequency doesn't change means, yeah, I have equal power. So this is a steady state. Okay, so this is when the system is operating at steady state. So at the steady state, I have some electrical power that's delivered, right? That's delivered to the grid. Suppose I have some mechanical power I put into the generator, and then they should equal to each other, right? At some angle delta zero, they're equal to each other. They're equal to each other. Okay. Any question up to now? Okay, so they're equal to each other. Now let's look at what happens when I change things a little bit. Okay, let's look at what happens when I change things a little bit. Okay, so they're equal to each other. Now let's try to change the picture a little bit. So this, remember, is my curve, and I'm at this point, PM, delta zero. So now when I'm at a point PM at delta zero, so let's say we increase PM by a bit. Okay, so let's say PM, the mechanical power you have into the generator, increased by a little bit. Okay, let's say this is increased by a bit. If this is increased by a little bit, right? So if this increases by a little bit, let's think of what happens in our system, right? So for example, you have wind turbine and you have, more wind. You suddenly have a gust of wind, you have increased mechanical power. So now I have as PM larger than PE, right? I have an increased amount. My mechanical power into the system is larger than the amount of electrical power I'm delivering to the grid. then what changes in the system? Let's say you have wind turbine, suddenly you have more power into the generator than you're delivering to the grid. So PM larger than PE. So then how does the system change? How does the variables change in the system? Any idea? So what happens when you have a generator and suddenly you put in more mechanical power? Intuitively.
Would EF increase slightly?
So let's say EF is not increasing. Let's say EF is determined by the current, right? By the exciter current. Let's say we're not increasing that. Or EF is already at its maximum. So where does this power go? Right? I have electrical power coming at one end. I have mechanical power going to the other end. I have more power going in than the power coming out. So where does my input power go? It has to go somewhere.
When those powers turn into heat, because it just wasted.
Not directly, no. It doesn't immediately turn into heat, right? It's not this power suddenly everything heats up. No, will eventually become heat, but not at a short time scale.
Is
So
it
yeah, go ahead.
reactive power?
Reactive power, I don't care, right? It's reactive power.
Okay.
It doesn't do work. So I don't care about reactive power at this point. Right. So so mechanical power, PM, is real power, right? It's active power. It's turning something. But I'm not taking this much power out of the generator because it's connected to a grid and let's say PM suddenly increases. So you have a turbine turning. So think about where does that power go? What happens to your turbine if you put in more power? And the power
Just
coming
go-
out?
It's been faster.
Right. So yeah, so I don't know who said it, but it spins faster. Your turbine spins faster because the mechanical power has to go somewhere and it goes to the mechanical rotation energy. Okay. So omega, what happens is goes up, right? So the rotation frequency goes up, right? So this PM becomes mechanical, becomes rotational energy. Right? So it has to go somewhere, goes to this. Okay. So frequency goes up. Then a frequency goes up. What happened to the angle? What is frequency actually? How is the frequency related to the angle? How is omega related to delta?
The omega is gonna get bigger if the frequency is higher.
The frequency is higher, the angle gets bigger, right? Because delta dot is omega, right? The time derivative of angle, right? The time derivative of angle is frequency. Okay. So any questions up to here? Okay, so I have more mechanical power, therefore my turbine spins faster. Omega goes up. But omega is, right, frequency is by definition the derivative of angle. Right, so angle is radians, frequency is radian per second. So it's time derivative. So omega goes up, increases, or omega. This means that so omega increases compared to a reference, right? This is compared reference, right? So then delta increases, right? So my frequency is faster, so my angle gets larger. But then PE equals to 3 VTEF XS sine delta. So at this point, if delta increases, the sine delta increases. So PE increases. So if I increase PM to this level, let's say by a little bit, then correspondingly, naturally, my angle will change to delta 1. Okay, so if I increase the mechanical power, then naturally in my system, so this leads to a frequency increase leads to a larger angle, but the larger angle leads to more mechanical, more electrical power being delivered to the grid. So therefore, PM equals to PE, right? My PE increases to balance PM. Any questions about this argument?
Wait, you said P is equal to PM. Can you explain that part again?
Okay, so, right, so omega increases, delta increases, right? Sine delta increases, so PE increases. So eventually, this increase will be equal to PM, and they will stabilize, they will balance out.
I see, thank you.
Any other questions on this? Right, so this is a good operating point, right? As small changes, for a small change, the system naturally balances itself out. Okay, so this is a nice operating point. On the other hand, let's look at this operating point. Right, so let's say this is PM. So let's say I can still operate, right? So let's say I've operated at delta 0 here. This is fine. If nothing changes, this system is fine. Right? We'll be outputting PM. That's fine. So, but let's say PM larger than PE, so PM increases. By the same argument, omega increase, delta increase. But then what about PE? Does this increase or decrease?
Decrease.
This decreases because you're at the other side of sine, right? So at this point, increasing an angle will decrease sine. This decreases. So PM minus PE, right? So this is even larger. PE. And this is a positive feedback loop. That's no good, right? Your omega keeps getting larger, your angle goes larger, but then the power you deliver to the grid actually goes down. So you get more power into the rotor, it will spin even faster. And this is, eventually this will either trip the protection of your generator, or if you don't have protection, just blow up your generator. So this is an unstable operating point, right? A small change means, system just runs away from this point. Any questions about this?
So between these two angles, then we mostly gonna use the left angle instead of the right, right?
Yeah, we'll never use the right angle. We'll never use the angle.
Okay.
In power system, you'll never see two buses with an angle larger than 90 degrees. That just does not happen.
What does it call again? Two buff?
No. So when you look at two nodes or two buses in a power system,
okay,
the angle between them is not larger than 90 degrees. This is almost never. This will almost never happen. or this will never happen actually. So I cannot think of a situation with this.
Yeah, just confused with the wording like that
Yeah.
uses. Thank you.
Yeah. Okay, any other questions about this?
So in the first case for the stable operating point, this will have gotten the angle like slightly closer to 90. Would you then like try to compensate to bring that back a little more down so you don't get too close to 90?
No, you don't bring it down because that may not be possible. So in practice, what happens is you have a constraint such that your angle be far away from 90. So normally when you're operating the system, let's say you're looking at through a transmission line or between a generator and the grid, your constraint is actually the angle needs to be much, much smaller than 90. So normally it's a 45 degrees angle constraint. Your max angle can only be 45 degrees apart. So under that constraint, even your angle slightly larger is still very far from 90. So that's sort of building safety margin there.
Got it. That makes sense. Thank you.
Right. So yeah, so that safety margin is to control that when you have disturbance, you don't even come close to 90 degrees. So in the system, actually, most likely, we're pretty much limited by this angle. A lot of times when we cannot transfer large amount of power from one part to another part, not because we can't generate the power, not because this will melt the transmission line or something or too much heat. It is because this angle is a problem. We cannot let the angle to be too big because the angle that's sort of unstable is the worst thing that can happen in the system. Right? You want to very tightly control this. Okay. Right. So this is when you solve. So when you solve this kind of equation, right? You may have a question that says, given PM, find the angle. Pick the smaller angle or pick the angle less than 90. Right? If you pick angle larger than 90, you'll be very heavily penalized because that is the unstable point, and being unstable in the power system sort of the worst thing you can do. Okay? Right? So when you solve the problem, you should know that when you find an angle, find it less than 90. You should not say an angle is larger than 90. That's kind of questions. Right, so this is sort of the stable steady state operating point. This is always to the left of 90 degrees. We'll see this again for induction generators, or for induction machines. But in power system, you have this quite a bit. There's sort of multiple solutions to the equations because the equation involves sine and cosine. There's sort of always, almost always more than one solution. You need to figure out which one is the stable one. So for this sort of small system, it's trivial. But for a larger bulk power system with sort of thousands of nodes, it's actually quite difficult to figure out whether it's actually stable or not. And that's a sort of very active area of research as to, to formalize this picture to a larger system. That's actually quite hard to do. We don't have a very good idea how to do that right now. Okay, so but for a small system, it's a very clear rule, less than 90 is stable. Okay. So of course you can operate things at 0, right? So 0 is just 0 angle. Again, sine equals to 0 has many solutions. Pick 0, right? Pick 0. Okay. And so then we sort of went through what happens with when you have a change in operating power. Basically, the idea is do not operate at more than this power. And when you're operating your generator, you should never choose this point, right? If you choose a PM, mechanical power, is more than the maximum electrical power you can produce, then bad things happen. Right? So this mostly happens in wind turbines. So that's why it's important to have pitch control to make sure the mechanical power coming into the generator is much less than the maximum power you can send to the grid because stability issues. All right, so this is the angle part. So of course we can, as many of you said, we can change EF. So excitation is just EF. So if you change EF, just the sort of obvious what will happen is the curves will go up, right? So this is EF1, EF2, here EF2 is larger than EF1. So you could change this excitation voltage in the system, but normally you have a fairly limited range to pick for this. Okay, so the range is not very large, the excitation. You can change the voltage a little bit, but not dramatically up and down. And this also is hard, the feedback loop on the voltage can be complicated. Right? So often still you want to make sure that your angle is much less than 90 to operate at a sort of stable operating point. All right, so let's do a question. Let's do a question here. So this question says that we have synchronous generators connect to an infinite bus. So let me add a 3-phase. Let's make this. So yeah, so a 3-phase synchronous generator is connected to infinite bus. You know the voltage at infinite bus. You know the excitation voltage, and you know the synchronous reactance. And so we say if the output power is 100 megawatts, compute the angle delta. Compute the angle delta. All right, so here the equation is simple. We just use the P equation. This is 3 VT EF XS sine delta. Okay. So if the question says a 3-phase synchronous generator, says three-phase generator, then to use this equation, right? So I can write 100 megawatt equals 3 times. Then what should I use for the value of VT if this is 3-phase? Right, so VT is 23 kV, but this is a 3-phase generator. So for this equation, what number should I plug into VT? Is it just 23 here? Is it just 23 kV? Should I just do this? And solve for delta? So we have a 3-phase generator and says the voltage is 23 kV. Which voltage is this thing referring to?
Is that line-to-line voltage?
Right, so this is a line-to-line voltage. So when you use this equation, you use 3 times VT times EF over XS. What you need to do is you need to convert the line-to-line voltage, right, to the phase voltage or line-to-neutral voltage. So what you need to do is divide by √3. This voltage is by √3. So you need to divide things by √3, then solve for delta, and then solve for delta. So here, when you solve it, you get delta equals to 20.35 degrees. Okay, any questions about this? So again, when you read voltage for 3-phase things, always remember they're line-to-line voltage. Okay. Always remember it's line-to-line voltage, right? So don't forget to divide by √3 when you should divide by √3.
Is that when the case for the problems that's given is the infinite bus?
So both voltages are line-to-line. Right, so the key thing is to say this is 3-phase. Right? So whenever you see the word 3-phase in a question, and if the voltages are not, it's not explicitly said what voltage it is. It's always line to line.
Oh, I see. Thank you.
Any other questions? Okay, so this is computing the angle, right? We can also compute the pullover power. So pullover is another, is equivalent to saying compute the maximum power delivered. So here the max power is 3VT EF XS. So here you assume the angle is 90 degrees, and you get this as 287.5 megawatts. Okay, so this is the maximum power. So of course, we can ask other questions. For example, if we reduce the internal EMF, right? So we reduce the excitation current of the generator by 10%. This means that EF reduces by 10%. Okay, so we can again compute what the angle is and what the maximum power is. So EF reduced by 10%, this means 25 kV goes to 25 times 0.9 kV. And we can repeat the calculations. We get delta equals to 22.47 degrees, and P max is 258.75 megawatts. Okay. Right, so this is sort of a style of question we have. Any questions about this? Okay, so next we'll look at the reactive power control. So actually, what time is it? Okay, so before we do that, let's take our break. So let's break until 3:30. Then we'll look at reactive power control, and we'll finish synchronous generators. And then we'll start looking at transformers. Okay, so let's take a break until 3:30. Okay, so let's get started again. All right, so far we have been looking at the active power, but we can also look at reactive power in the reactive power produced or consumed by the generator. So here we have PE as VT EF XS. So let's say I want to produce 0 active power. So I can set delta to be 0 degrees, and this I get 0. But then Q becomes, right, Q is 3VT over XS EF cosine delta minus VT. Cosine of 0 is 1. So this is 3VT XS EF minus VT. Right, so this is my reactive amount of Q, reactive power I produce and send to the grid. So if EF is equal to VT, I have Q equal to 0. Right, so in this case, you have both the active and reactive power to the grid being 0. You can match the voltage and set the angle to be 0. So of course, you don't have to operate this way. Right, you can still keep your reactive power 0. That's fine. Because you can still keep your active power 0. You can still keep delta 0. But then what you can do is you can have EF larger than VT. Then what this does is we have a Q larger than 0. We can have a Q larger than 0. And this you can think of as the generator, a capacitor, because you're producing reactive power. So this is overexcited operation, right? You're producing reactive power while not producing any active power. So equivalently to, you can have EF less than VT. Then you can have EF less than VT. Here you have Q less than 0. And here you behave like a inductor. Okay, so it's quite flexible. Right? You have sort of both, as the synchronous generator is quite flexible, can operate both as a capacitor or inductor, can both generate or consume reactive power. Okay, so P normally is positive, but Q can be positive or negative. Right? So also at the same time, given P, right, you can change your key. Okay, so you don't have to operate as, so given active power does not constrain you too much from operating at different reactive powers. Okay, so it's sort of the synchronous generator has a benefit of both producing and either consuming or producing reactive power. When we get to something like an induction machine, we'll see that's different for an induction machine. Turns out an induction machine can only consume reactive power. But for synchronous machines, reactive power flow can go both ways. Okay. All right, so then the last thing we want to look at for synchronous generator is basically what happens when you're connected through a transmission line. Okay, so a lot of times when you have a generator, you don't have the generator connected directly to the infinite bus or to the grid. Right? You have a generator, there's a terminal of the generator, you have a cable, you have a transmission line that connects the generator to the infinite bus. Right? So thus the transmission line here is basically just another synchronous reactance. So now the thing is that we have basically 3 voltages to look at. Right? We have EF, we have the voltage at the terminal of the generator, and then we have voltage at the infinite bus. And the idea is, this is normally V0 is V0 at angle 0. This is a reference. And then we can figure out what is the terminal voltage and what is the EF, right? And the voltage on EF, okay? All right, and the equation doesn't change all that much. It's basically, you take whatever was XS before, you replace it by the equivalent, you just replace XS by XS plus XL. Right? So it doesn't really doesn't change all that much. Okay. So this is many equations go from XS to XS plus XL. Right? It just seems to have a bigger reactance, basically. When you're looking from the grid perspective, it's the same generator, except the synchronous reactance got larger. And also when you connect to a transmission line, what happens to P max? Does it increase or decrease? So compare to a case when you have no transmission line. Here, when you connect to a transmission line, what happened to P max?
It goes down.
Goes down, right? P max decreases since before, right? So this P max is proportional to 1 over XS plus XL. Okay, so you're adding some reactance to it, and then the maximum amount of power you can deliver goes down. Okay, so this may be a little bit counterintuitive, because if you're just thinking about sending active power through the line, you're thinking as, the line is purely inductive, it doesn't consume any power, there's 0 losses on the lines. Somehow it may not seem like it should limit the amount of active power you can transfer to the grid, but it does. right? Just because you have a larger synchronous reactance, that actually will limit the amount of power you can transfer to the grid. Okay, so this is just something to keep in mind. As this line, even though there's no loss on the line, even though it's just an inductor, from a circuit perspective, this limits sort of the maximum power and the operating point that you can operate at. Right? Okay. But then the equation again, because there's not much to say about the equations, right? Often as you define X, the equivalent reactance as XS plus XL, you multiply by, then everywhere you see XS, you just substitute this in. Okay. So we can do a couple examples to see this. Right, so this is the same as before. I have a 3-phase synchronous generator, infant bus voltage 23 kV, transmission line 1 ohm, synchronous reactance 2 ohms. So here we're going to adjust the EMF to be 28 kV. We want to figure out, at what angle do you deliver 100 megawatt. So here what we have is P is equal to 3 times VT times EF. Now instead of just dividing by XS, we need to divide by X, which is the sum of the line reactance. Some line, right? So here we're going to compute the terminal voltage of the generator. Okay, so the way we're going to compute the terminal voltage is first we'll figure out the angle of EF, then we can figure out the current, right? Then we can figure out the terminal voltage. Okay, so let me be a little bit clear on what we're trying to compute. As we have an EF here, there's some synchronous reactance XS, there's some line reactance XL. What we want is, I want to get this VT. So this is find VT. So this question is asking us, can you find VT, this voltage? So here, the way to do it, first we'll figure out what EF is, and such that we can compute the current flowing on this branch, right? We can compute current flow. We can compute current flow, we can compute the voltage drop across XS, and then we can figure out, so there's many ways we can figure out what VT is, right? We can, once we know the current, we can figure out VT. So to figure out current, first let's compute the angle. So this is P equals to 3V0 EF X sine delta. So this is 100, 3 times 23 divided by root 3, 28 divided by root 3, 1 plus 2 sine delta. Delta is 27.76 degrees. Okay, so this is the angle. Now we can figure out the current, right? Now we can figure out the current. So the current, the per phase current is the EF minus V0 divided by JX. So this is 28 over root 3, angle 27.76, 23 divided by root 3, angle 0, J1 plus 2. This is 2.53. Angle minus 7.5 degrees kiloamps. Okay, so this is the current flowing this branch. So then if we figure out is VT, once we know the current, of course, we can figure out VT. This is V0 plus the amount of current times JXL, right? So current times impedance give you voltage, and substitute this numbers in, we get 13.85, angle 10.44 degrees kV. Any questions up to this point? Okay, so for this VT, is that the line to line or line to neutral? Right, so this is again three phase. Which voltage do we compute here?
Line to neutral.
Right, this is line to neutral because we use a phase curve. So this is line to neutral. So we can have the line to line just multiplying this thing by √3. So line to line gives this is 24 kV. So when you do a question, let's say on the final, if you write a voltage, you can either indicate it's line to neutral or line to line. If you do not say what voltage it is, and it's a three-phase system, then it's assumed to be line to line if you don't say what it is. Okay, so you can either decide to say it's line to neutral, or just compute the line to line one, and right. So for safety on the final exam, when you write a voltage, always write as a line to neutral or line to line. Okay, so you don't have to always convert to line to line. You can leave it in line to neutral if you want, but you need to say it's line to neutral. Okay, you need to specify what voltage you're computing for a three-phase system. Any questions? Okay, so this is the line-to-line voltage. We can also compute the reactive power at the infinite bus, right? So this is asking what is the Q at the infinite bus here. Well, for Q, we have this equation. Q is 3V0 X EF cosine of the angle minus V0. So you plug in all the numbers into this thing, right? So this is √3, 28. 23 over √3 times 3 over √3 cosine 27.76 minus 3. Plug all this in, you got 13.62 megawatt. So this is the reactive power you have at the infinite bus. Right? This is the reactive power you have at the infinite bus. So of course, this reactive power at the infinite bus, right? Before the reactive power gets to the infinite bus, it's also consumed by the transmission line, right? Also consumed by the transmission line. Right? So for example, we can compute the reactive power consumed by the transmission line, because again, if you look at the circuit model, this reactance consumes some reactive power. So this is QL. So let's denote this by Q0. Q output, QO, this is 3A squared. XL, this is 3 times 2.53 squared times 1, 19.25. Any questions up to here? So these are fairly standard calculations you'll be asked to do for a synchronous generator. Okay, so the last question, or you may have, is that compute the reactive power at the terminal of the generator. Okay, at the terminal of the generator. So what this means is compute the reactive power here. Right? So this is your terminal of your generator. So we know the reactive power at the output to the grid, but we also want to know what is the reactive power at the terminal of the generator. So to compute this, what we can do is we can use, this is the reactive power at the output plus the reactive power consumed by the transmission line. This is 32.87 megawatt. Any question with this calculation? Okay, so almost surely you'll see this type of question on the final, or sort of a variation of this question on the final, right? So you want to get very familiar with this type of questions. As computing the, the P and Q at the output at the infinite bus, or at the terminal of the generator, compute the currents, computing the reactive powers, this kind of thing. So this is a very common type of question you see on the final. Okay. So if I have a question, please ask. If you don't, just get familiar with this type of question, with this type. Okay. So the last thing for this synchronous generator, the last thing we'll say is something about, again, as we hinted before in the lecture, the transmission capacity, right? So because if you look at the transmission capacity, if you look at the synchronous generator, right, you're limited by this X, right? You're limited by this number X. So often you want to, if you want more power transfer capability, if you want to send over larger P, you need to do something about this X. Right? So there's two ways. Right? So there's two ways you can do it. There's two things you can do basically with this X. One is you can just add a capacitor to this transmission line and try to cancel out the value XL. Okay? You can add a capacitor because your equivalent reactance now is a sum of the inductors subtract the capacitance, right? Subtract their capacitive reactance. Okay? So this gives you a larger P max you can have. Okay? So for example, we can do a calculation, right? We can say, okay, suppose we have this system, infinite bus voltage is 230, EF of 210, and the synchronous reactance 2 ohm, inductive reactance 10 ohms. We want to find the capacity of the system, and we want to find this capacitor install to increase the maximum power transfer by 25%. So if you look at the equation we have as P max, this is 3 EF over X. This is 230 times 210 and plus 2. This is 4.025 gigawatt. Well, if I want to increase this by 25%, then basically what I need is 3 times 230 over root 3 times 210 over root 3, 10 plus 2, subtract XC equals 4.025 times 1.25. Thus, I get XC as 2.4 ohms. Okay, so a capacitor has a capacitance of 2.4 ohms. So is this a large or small capacitor? Is this easy to have? Is it easy to buy a capacitor, let's say of 2.4 ohms? Any ideas of how large this capacitor is? Anybody work with capacitor regularly? Okay, so this capacitor in a 60 Hertz system, this is roughly 1.1 millifarad. So how big is a 1.1 millifarad capacitor that carries a lot of current? Anybody have an idea of the size of capacitor? Okay.
Pretty small.
No, this is a extremely large capacitor. So the farad, right? The unit farad is a very large unit. So a 1 farad capacitor is almost never seen. A millifarad is a very large unit. especially for a capacitor carries a lot of current. So this is a large capacitor, a very large capacitor, a very costly capacitor as well. You need a special room just to house the capacitor of this size. Okay, so most capacitor won't survive the current. So you need a pretty special capacitor to do this. So this kind of capacitor is only used basically in very large substations. Okay, so it's not like right? So if you look at the equation again, if you just draw the diagram, you say, okay, why don't you just add a capacitor to cancel this out? The answer is it's not easy to add a large capacitor. And large capacitors are expensive, hard to build, require a lot of space. So we do series compensation, but this is done so rarely or only in very large substations. Right, so we do this. So another way to do compensation, which is actually maybe easier, is to just add a parallel line. Just add a parallel line. Because what happens when you have a parallel line, as the reactance goes down, right? Putting two lines in parallel makes the equivalent impedance reduces. Okay, so you add enough, you add a parallel line, XL appears to be smaller. And this is more common in practice, as you just build a double line. And then you can transmit more power this way. Okay, so you have a transmission line pole, instead of carrying one circuit, one line, you just put two lines on it. And this is, this increases the maximum power transfer you can have in the system. Okay. Right, so both are strategies, but the building parallel lines cannot cancel out XS, right? Can only make XL smaller. Adding capacitor can cancel everything, but normally we cannot add too large of a capacitor. Right, so again, this transmission capacity, this sort of P max, comes up quite a bit in power engineering. Comes quite a bit in power engineering. And sort of the reason comes up is different, right? So it's somewhat different. So for a short transmission line, this comes up, right? You don't want too much power to flow, is because when power flows, more power means more current. More current means you heat up, right? It means that I squared R, you have more losses. These losses are heat on the conductor. Right? So when you heat up a conductor, because thermal expansion, the conductor actually gets significantly longer. Right? Just a warmer conductor is a longer conductor. So when you suspend this conductor, right, the conductor gets longer. The length the conductor again has to go somewhere, and the conductor sags. And when it sags, if it gets too close to a tree, you may create a short circuit because a current tries to jump through a tree. Right? This may jump through a tree. Okay. So this is a situation we try to avoid, right? And actually cutting trees or doing tree clearing is a big part of utility or power company. So there's dedicated units in power companies that the whole job is to make sure you don't have trees growing too close to power lines. Okay, and again, this power line, once it heats up, will sag. It's very windy, will sway around. If there are ice on the lines, they also get heavier. They may also sag. So you want trees to be far away from power lines, and this will limit your power transfer. Right? This will limit your power transfer. Okay. So normally, this kind of thermal limit limits how much power we can have. And when you have an overload, what it looks like is you have a short, and then you just have a breaker that may open. Okay? You may have a breaker that opens. So that's also the reason why you see this kind of conductors. You see conductor, you don't see a sort of big conductor. You don't see a big cable going through this way. but often you see this sort of conductor bundles that try to open up more space for heat to dissipate, right? For to have better dissipation of heat. So this is also another reason that limits your amount of power you can transfer. So power transfer are limited by either the heat you generate or the synchronous reactance or the maximum power transfer you have. Any questions on this?
What is the reactant part called again? Synchronous reactant?
So reactance is synchronous reactance. So this is the excess we have here.
Synchronous reactant.
Synchronous reactance. Yeah. So this is sort of when you design transmission lines, there's a lot of actually sort of practical issues going to transmission lines. But they're limited by the maximum power and also limited by the heat they generate on the lines. Any questions about synchronous generators? Okay, so if no questions, then let's introduce transformers, and we'll get into the equations for them later. But let's just have a look at transformers, right? So this flows naturally from our generators. So when we talk about generators, so a generator typically do not generate at a very high voltage. Okay, so if you directly measure the voltage coming out of the generator, it's not terribly high. So if you measure the terminal voltage that comes out, just because the way that we have a exciter, but you don't boost the voltage up by that much. So you have a voltage in the thousands or tens of thousands of volts, but not in the hundreds of thousands of volts, which is where we want to do transmission of. So a transformer's job is basically boost the voltage, reduce cost, right? So as from the generator's end, this is job is the transformer boosts voltage, reduces losses. To reduce losses is similar to reducing cost. Then at the receiving end, it lowers voltage for safety reasons. Right, so at your house, you want voltage in the hundreds of volts. This can also create isolation. Often we want to isolate a system, so want two parts to be isolated to each other. So we use a transformer. This can also be used to do impedance matching. Okay, so a transformer is quite the common equipment in the system, right? And they're used all over the place. So basically, after you come out of a power plant, there's a big transformer that boosts the voltage up to pretty high voltage. Then successively, this voltage goes down until the voltage that's used in our homes. Right? And if you look at the pictures for transformers, you have very large transformers. This is a transmission level transformer. So these are very large transformers. You have to cool them. You have to. They are very costly. They cost for millions of dollars. And then you have distribution transformers, which are smaller. So these are the ones you see if you walk around. You'll see sort of this fenced area, and you have this transformers inside. These are distribution transformers. So they transform from tens of kVs to hundreds of volts. You have transformers mounted on poles that might step down the transformer by a ratio of 2 to 3. And then you have sort of transformers you see when you walk around neighborhoods these are used to boost voltage or do isolation, or just step the voltage down by a factor of 2. Okay. And then you have really small transformers that which we don't use in power engineering purposes. So for us, this is sort of the smallest transformer you'll see. Okay. So from next time, we'll look at some equations. We'll write out all the equations for transformers. The equations for transformers are actually quite simple, quite simple equations. The circuits we get are fairly simple circuits. And then after transformers, we'll go to a induction machines, which actually just look like a transformer. If you have an induction motor. Okay. So let's stop the class here today. Next time we'll finish transformers. So I'll see you on Wednesday if we have no questions. So if you have questions about homework, you feel free to ask.
Thank you, Professor.